Bismillah ar-Rahman Rahim. This lecture is the continuation of the previous lectures in which we have already discussed the ionizing radiation or the energy loss by the ionization or by ionizing radiations. So, just I'm going to repeat over here. Ionizing radiation is the radiation that has sufficient energy to remove the electrons from atoms and creating the ions. These are called the ionizing radiation, and all the alpha, beta, and gamma radiation are the ionizing radiation because they have the ability to ionize the matter. That's why they are called the ionizing radiation. So they are classified into two groups. One is the particle and other one is the photon. And the particle we have already discussed in the different videos. So please watch again if you want clarification on the interaction of the ionizing particles in the form of the particle that mean alpha, beta, and beta is the positron and the negatron. But here in this lecture, I'm going to explain the energy loss by the gamma rays and the X-rays, and both are having the same behavior. But here I'm going to discuss in more detail about the gamma radiation, which is going to act as the photon. So these are the particles, and gamma ray are considered as the photon. So let's see what is happening with the interaction of the photon with the matter and its loss of energy. So there are three possible occurrences when gamma ray photons pass through the matter, and one is the no interaction at all. That means the photons travel through the material and it is not going to hit with the electrons or the nucleus. So there are only the matter in here it is the electron or the nucleus. And one possibility is if this gamma ray is not having any interaction with the nucleus or the electron, then it is called as the simply the transmission. It is transmit through the material. So other is the photon travel until it hits something, either an electron or the nucleus. So there may be the possibility of the absorption and the scattering. So there are the several type of interaction have been observed. So I am going to discuss one by one all these in detail when there is the interaction of the gamma ray with the electron or the nucleus, or you can say the absorption or the scattering. So the first we have the different processes over here. One is the photoelectric effect, and the second one is the Compton effect or the Compton scattering, and third one is the pair production. Actually, these are the processes associated with the gamma rays photon interaction of the gamma ray photon with the matter, or you can say if the gamma ray is interactive with the matter, it is going to lose its energy by photoelectric effect or the Compton effect or the pair production, or the the three process may be simultaneously occur at a time. So the first one is the photoelectric effect. As you know, with the word photoelectric, that means the bombardment of the photon and the removal of the electron. So this process is called the photoelectric effect. But there is certain limitations here. So photoelectric effect involves the emission of an orbital electron with the kinetic energy equal to the difference of the interacting gamma ray energy and the binding energy of the emitted electron. So this is very important. Let's suppose this is the matter or the material on which this gamma ray is going to interact, So if the frequency of the light or the frequency of the gamma ray is lower than the certain value, this frequency mu naught is the threshold value. That means the minimum value required for the removal of the electron. If the gamma ray is having less frequency as compared to the threshold frequency or the minimum frequency, then there is the no ejection of the electron. You can say the gamma ray is going to fall on the matter, but there is no removal of the electrons. So electrons are not ejected over here. So when the frequency of the gamma ray is more than a certain value or is equal to the threshold value, then there is the removal of the electron. So this is the photon, and removal of electron is the matter. So when electron is removed, of course, it is going to move with a certain kinetic energy because of having a speed or the velocity of this electron, and this is half mv square. So it depends on the actually what would be the kinetic energy of that electron. It depends how tightly electrons are held with this matter and what is the frequency of the incoming gamma ray. So some of the energy is used to remove the electron, and the rest of the energy which is having with the gamma ray is imparted to the electron, and the electron is removed with the sum of the kinetic energy, which is the half m square. And this is the difference of the electron gamma rays energy and the binding of the emitted binding energy of the emitted electrons. It depends on how much tightly these electrons are bind with the matter. So in this process, incident gamma ray is completely absorbed. So this one is the process when the gamma rays are completely absorbed and are having a sufficient energy, then the electrons are removed from the metal, and this process is called the photoelectric effect. So the gamma ray is going to lose its energy to remove the electrons, and that is the loss of the energy by the gamma ray by observing the photoelectric effect. And this is in detail of the photoelectric absorption, and the example is the this is the iodine 131, and look at the detail. So what would be the binding energy, how it is going to affect the gamma ray, what would be the energy, what should be the energy of the gamma rays to remove the electrons. It depends on the binding energy of the electrons with the nucleus. So this binding energy it is given over here. For the K shell, it is 34, 5.5.6, and approximately 0. So 66 kilo electron, this is the photo electron energy, which is removed from here, and incoming or the incident photon is having the 100 kilo electron volt. So what I'm going to discuss over here, because these electrons present in the K shell have strong interaction with the nucleus. That means because these electrons are very close to the nucleus, so these are tightly attached or tightly binded with the nucleus. That's why the binding energy is more as compared to the other electrons. So binding energy of the K electrons are more, and it is 34 as compared to the other electron present in L, M, and N shell. So let's suppose it is the 100 kilo electron volt energy is required, and this is the, let's suppose this is the lambda 1. Lambda 1 mean energy required to remove the electron from the K shell, and this is having the wavelength. So let's suppose this is the wavelength, and wavelength mean energy and wavelength are inversely proportional to each other. This is according to the Planck's theory. E is equal to h mu. Quanta of light is there, and mu is the c over lambda. So lambda wavelength is inversely proportional to the energy. Less will be the wavelength, more will be the energy. So this wavelength is small. That means you need high energy to remove the electron from the K shell, because binding energy of the K electron is more as compared to the other. So when you are moving to the uh, L shell, so look at the wavelengths. No wavelength from here, it is small. No wavelength is going to increase. That means now the wavelength is going to increase, having sorry, the so wavelength is going to increase. That means energy is going to reduce. That's why, because the electrons present in the L shell are having uh, small or low binding energy as compared to the electron present in the K shell. So less energy is required to remove the electrons. So the wavelength is more, the energy will be small. The small energy, that means longer will be the wavelength, and it is indicated over here. This is the wavelength, and look at, this is the wavelength for the lambda 2 from the air shell. And similarly, if you go to the M shell, the binding energy is again is lower as compared to the M shell, and that's why the wavelength is large as compared to the previous case, and simultaneous is going to increase, further increase, because the energy, binding energy, is again very small as compared to the M shell in the N shell. So wavelength is going to increase. So this is the order of the wavelength, and energy is given over here. The C is having, C is there, and of course this is again more, but here I'm going to explain with the L, M, and N shell. Of course, K shell is having more. So from when the electrons remove from the uh, L to the K shell, or moving from here, or it may remove from the K shell or the L shell, then this would be the energy from the C. This is from B, and this is zero point 0.6 from the A. So these are the actually this is for the characteristics X-rays, but similar behavior is with the gamma ray energy, because the wavelength and energy are inversely proportional to the each other. So what would be the order of the wavelength? This would be the order of wavelength. So wavelength 4, this wavelength 4 is large, having the high value. That means the energy is small. And wavelength 3, then this is having less value, then energy will be more, and this is again, this is greater than this, and this is greater than this. So highest wavelength in case of the lambda 4, and least wavelength in case of the lambda 1, as indicated over here. Or you can say there would be a high energy in case of the lambda 1, or low energy in case of the lambda 4. So this would be the energy required for the removal of the electrons from the KL and M shell. It depends on the energy of the incident photon, and simultaneously this is going to depend on the what would be the binding energy of the electrons held with the nucleus. So this is all about the photoelectric absorption in case of the uh, iodine 131. The second process is the Compton effect. So remember, photoelectric effect is the absorption phenomena, and Compton effect is considered as the scattering phenomena. So Compton effect occurs when the interacting gamma ray imparts some of its energy to an orbital electron, so that the bound electron cross crosses the binding energy barrier, and consequently an orbital electron and less energetic photon of the incident gamma ray undergo angular scattering. So this is very clear representation. Again, I'm going to explain over here. This is the gamma ray. Gamma ray is having the incident wavelength. When it's going to target this target electron which is at the rest position. So this is going to the energy required, some of the energy required to remove the electron, and the other energy which is going to be scattered over here. So and that means what is the difference from the photoelectric effect and the Compton effect. This gamma ray is not fully absorbed in the material or the matter to remove the electron, but uh, the part of energy is absorbed to remove the electron, which is called the recoil electrons, and the rest of the energy that is having the gamma ray is going to be scattered, and this is called the scattered photon. And again, look at the wavelength. This is the incident photon, this is the wavelength of the scattered photon. Of course, this is having more energy, and this is having less energy. So the wavelength of the scattered electron will be more as compared to the wavelength of the incident photon, because both are having a inverse relationship, because the energy is inversely proportional to the wavelength. So this is the Compton effect. Again, have a clear picture over here. Let's suppose there is an incident photon having this wavelength lambda 1. When it collide with the electron, when it hit the electron present in the shell, that means if it is the M shell, then Compton effect is going to happen, and this is the removal of the electrons, which is called the Compton electron, and the rest of the energy is scattered with the angle which is called the angle of the deflection, because this is the incident photon. It has to pass through the same direction, but when it is hit with the electrons, it will remove the electrons, and some of the energy is used to remove the electron, and the rest is going to be scattered. But this wavelength is large as compared to the incident photon. So that's why lambda 2 will be more as compared to the lambda 1. Or you can say the energy of scattered photon will be less as compared to the incident photon. Again, the equation is given over here. There is the inverse relationship between the energy and the photon. The third process is the pair production. Again, this is the incident photon, gamma ray, when it is going to hit the nucleus, and it will produce the pair in the form of the positron and the electron. So that's why the production of the positive and the negative, this is called the pair production. That means pair means one positive, one negative. One positive is the positron, and one negative is the it is the, of course it is the electron, or you can say this is the negatron, and having the positive charge and the negative charge. So the condition is given over here, because contrary to the previous two examples, photoelectric effect and the Compton effect, this is the third process in which the interaction of the incoming gamma ray is with high electric field in the vicinity of the nucleus of the atom. So this is the one of the important, if it is going to hit with the nucleus of the atom, and this type of interaction is possible when gamma ray is having a minimum energy of 1.02 mega electron volt, and this is the condition. If it is less than as compared to 1.02, then this process is not going to happen. And why this is the reason, this is 1.02, I will explain in the coming slide. and I have a little bit explained in the emission of the positron before. So this electron and positron pair is produced with this energy. This effect is thus a reversal of the annihilation process because here electron pair is produced by the loss of the 1.02 mega electron pair energy. So this is actually opposite to the annihilation process, and annihilation process I have explained in the previous video. This is associated with the positron, and when the positron is coming from the nucleus, it is going to hit with the electron present in the outer shell, and they are going to be annihilated, and with the production of the energy, which is the 1.02. That means it is equal to the mass of the two electron, because the positron and the electron are having the same mass but only having the different charges over there. So let's look again what is the pair production process again. So if the gamma ray is having 1.02 mega electron energy, and then it is going to interact with the nucleus. So this condition is important. Look at what is the difference between the first two example, where the gamma ray is going to hit the electron present in the outer shells. It is going to remove the electrons in case of the photoelectric effect or the Compton effect. But pair production is associated with the nucleus. So if this gamma ray with energy 1.02 is going to hit the nucleus, it is going to remove the negatron and the positron. Negatron positron is called the pair production. So, uh, but what is happening again? As we have discussed before, this positron has a small pathway, and when it is it will interact with the free electrons present in the outermost shell. This is going to be annihilated, and this process is called the annihilation process or the annihilation reaction. That means this positron having positive charge is going to interact with the negative charge, and this is going to disappear. This disappearance is the annihilation process, and again simultaneously it will produce two gamma ray having of 0.51 mega electron energy, and some of these electron energy is the 1.02 mega electron volt, because there is a disappearance of two electrons, and each electron the mass is equal to the energy of the 0.51 mega electron volt. That's why this process is inverse to the annihilation process. If it is, this is going to disappear with the production of the 2 mega electron volt, 0.51 mega electron volt, or you can say 1.02 mega electron volt. That means with the same energy of the gamma rays, when it is going to interact with the nucleus, this will again the positron and the negatron. That means reverse of the this process. So coming to this one, the conclusion: incoming photon must have the energy at least 1.02. This process is a conversion of energy into the matter, and then matter back to the energy. This is the energy when these protons and positron and neutron are produced. That means this is the convert of the energy into the matter, and when annihilation process is happened, then that means this matter is again converted into the energy, converted back into the energy. So an incoming photon of 1.02 mega electron volt or greater interacts with the nucleus of an atom, and the transformation of energy results in the formation of two particles: negatron having negative charge and positron having the positive charge, as I have explained before. So, what are actually the positrons? It is considered as the antimatter because it will interact with the electron to disappear, to annihilate, and the process is called the annihilation process, and that's why this is considered as the antimatter or the antimatter, and they do not freely exist in the nature because having a short path length, and they will interact with the electrons to start the annihilation process. They will interact with the first electron, the counter, and an electron and the positron destroy each other during the interaction, and this process is called the annihilation reaction. And further, this converts this process actually converts the matter back into energy, and the both positron and the electron disappear during the annihilation process, and two gamma rays are released with the energy of the 0.51 mega electron volt. And this is the overall conclusion what I had explained before. So see you in the next video.